Hello. In this video, we are going to derive the sigma molecular orbitals of methane and methane-like molecules using the projection operator method. The first step in any chemical problem is to sketch it out. Here, we recall that the point group symmetry of methane is TD, the tetrahedral group. We are going to exploit the fact that we can inscribe a tetrahedron inside a cube as shown. Sigma 1, sigma 2, sigma 3, and sigma 4 are the 1s orbitals on hydrogen. The carbon atom, which would be at the origin of the axes here, is not shown. The first step is to derive the so-called group orbitals, the linear combinations of orbitals on the hydrogen that have the symmetry of the molecule. As a final step, we will determine which atomic orbitals on carbon have the correct symmetry to interact with the hydrogen group orbitals. It may also be useful, before you go any further, to consult the character table for the point group TD. We now show where each of the symmetry operations of the group TD are with reference to our diagram. The first operation is E, the identity, which we thought of as no movement at all, or a rotation of 360 degrees about one of the axes. There are three C2 operations. C2 involves a 180-degree rotation around an axis. Here is shown the C2 about the x-axis. Here is the C2 180-degree rotation about the y-axis. And here is the C2 about the z or z-axis. There are 6 S4 operations. S4 is an improper rotation. It consists of a proper rotation of 90 degrees followed by reflection through a mirror that is perpendicular to the axis of rotation. So here we see a 90-degree rotation about the x-axis, and then the position is reflected through the mirror, which is shown in gray. So this is the first of the S4 operations, and by convention, we consider the rotations to go counterclockwise or anti-clockwise. Here is a separate S4 operation where we rotate 90 degrees clockwise. This can also be referred to as S4 to the minus 1 because it's the inverse of S4, or it consists of 3 S4s in the anti-clockwise direction together, so we can call it S4 cubed, and that is the notation that we will use later in the derivation. Here is the third S4, we have a 90-degree rotation around the y-axis, followed by reflection through the mirror, which is shown in gray. The fourth S4 is along the same y-axis as the previous S4, but in the opposite direction, so we can consider it S4 to the minus 1 or S4 cubed. The last pair of S4 operations go about the z-axis. So here we have S4, which is a C4, a 90-degree rotation, followed by reflection through the plane shown in gray. The final S4 goes along the same z-axis as the previous S4, but rotates 90 degrees in the opposite direction. Next, we have 8 C3 operations. C3 is a proper rotation of 120 degrees, and it is easy to find in a cube because it rotates about an axis that is a diagonal of the cube. We realize that there are 4 diagonals of a cube, so just like the S4 operation, C3s come in pairs. There is C3 and then C3 squared, where we do 2 C3s in a row, which is identical to doing a C3 in the opposite direction. So again, we have the idea that C3 to the minus 1 is often known as C3 squared. And this is the first of the C3 operations. In this and the next 2 diagrams, please see where the C3 axes are in relation to the molecular orbitals and to the geographic features of the cube. Recall that each of these axes accounts for 2 C3 operations. The final 6 of 24 symmetry operations in the group TD are the dihedral mirrors, which we abbreviate as sigma sub d. Note here that sigma refers to it being a mirror and does not refer to a sigma type molecular orbital. In the diagrams, the mirrors are represented by using gray lines. Notice that each mirror goes through 2 opposite edges of the cube and bisects opposite faces of the cube. In this and the next 4 diagrams, please see the remaining dihedral mirrors in the point group. Next, we create a table that has the same types of heading as does the character table for the point group TD. We have colored the number of symmetry operations in each class blue. And we've added a number 1 to show the implied number of identity operations, which is always 1. What we are trying to do here is to generate a reducible representation for the sigma bonding in the group orbitals on hydrogen in methane. What we do is go for each column, each class of symmetry operations, and see how many of the sigma orbitals 1 through 4 do not move under the symmetry operation. For the identity operation E, all 4 orbitals stay exactly where they were, so we have a 4. For any of the C3 operations, the C3 operation goes through one of the sigma orbitals, so therefore one of them will not move and the other 3 will. So we have a character of 1. For the C2s and the S4 operations, every single one of the sigma orbitals moves somewhere, so we have characters of 0. Last but not least, for any one of the dihedral mirrors, 2 of the orbitals will lie on the mirror and therefore will not move, and 2 of the orbitals will move. So we put down in red the number of orbitals that don't move under the symmetry operation. And note that those particular characters for the reducible representation gamma sigma are all shown in red. Our representation gamma sigma is a reducible representation, which means that we can reduce it. We can show that it is a linear combination of irreducible representations from the group. The way to do this is through a mechanical formula, which we've shown in detail, starting with the first irreducible representation in the group, which is A1. So we always divide through by 1 over the order of the group the number of symmetry operations. Since there are 24 symmetry operations in TD, we always multiply by 1 divided by 24, which is equivalent to dividing everything by 24. And then we have a number of terms. The first factor in each term is, first is a number in red, which we see is the character for the reducible representation. The second number, which is shown in blue, is the number of operations in the class. So we see for the first case that the number of operations in E is 1. And the number in green comes from the character in the character table for TD. And for A1, the character under E is 1, so it's shown in green. Now you'll notice that we have 3 sets of terms, while there are 5 characters in the reducible representation. Here we're using the fact that if you multiply anything by 0, you get 0. So you can simply ignore any of the characters that are 0 in the reducible representation, the 2 red zeros. Now also notice that when we multiply these together, 4 times 1 times 1, plus 1 times 3 times 1, plus 2 times 6 times 1, inside the braces we get 24, so 1 over 24 times 24 equals 1. This tells us that there is one A1 irreducible representation included as a linear combination in gamma sub sigma, which is a reducible representation. As a double check, when you get the number of A1s, the number has to be either 0 or a positive integer. If you ever get a fraction or a negative number, you have made a mistake. The only possibilities are non-negative integers. So we see by this process that there is one A1 in the reducible representation. Then we proceed to the second irreducible representation that we find in the character table for TD. So we always begin with 1 over 24, and then we have 4 times 1 times 1, because 1 is the character in the character table for the E operation in the irreducible representation A2. Then for the second set, the 1 times 3 times 1, this refers to the characters for C3. And the final case, we see the 2 times 6 times minus 1. That is because the character in the character table under sigma d is a -1 for the irreducible representation A2, whereas it was a positive 1 for the irreducible representation A1. As a labor-saving device, you'll notice when you start to do this that the first two factors in every term will always be identical because they refer to the reducible representation and the number of operations in the class. The only number that will change will be the third number, the number in green, because that number depends upon the specific irreducible representation that you're working with at that time. So if we do this procedure, for the irreducible representation A2, we get a number of 0, which tells us that there are no A2s in the linear combination of the reducible representation gamma sigma. The third irreducible representation is called E because it is a doubly degenerate representation. So again, we have our 1 over 24 because 24 is the order of the group. And now we see in the first set of factors 4 times 1 times 2 because under E, the identity operation, for the E doubly degenerate irreducible representation, the character is a 2 and not a 1. Then we proceed with 1 times 3 times -1 because -1 is the character for C3. And then the character for the dihedral mirror sigma d is 0 for the E irreducible representation. So that gives us that there are no E's in gamma sigma. Next is the T1 irreducible representation. And we notice we proceed as we did before, but now seeing that the character under the identity operation is a 3. And this is because T refers to a triply degenerate representation. So in the first term, we have 4 times 1 times 3. The second term is 1 times 3 times 0 because the character for the class 8C3 is 0 for the irreducible representation T1. And then for the operation, the 6 sigma d operations, the character is a -1. So that's why we have for the final term 2 times 6 times -1 with the -1 being in green. And again, we get that the result of this computation is a 0, which tells us that there are no T1 irreducible representations in the reducible representation gamma sigma. The fifth and final irreducible representation in the group is T2. So we continue as we did before. We notice that under the E operation, the character is a 3 because we have a triply degenerate representation. So our first term is 4 times 1 times 3. The character under C3 is a 0. So our second term is 1 times 3 times 0. And then for our final term, we notice that the character for sigma d in T2 is a positive 1. So our final term is red 2 times blue 6 times green 1. And we get that the number of T2s that are in the reducible representation is equal to 1. This means that we can now write down that gamma sub sigma is equal to 1A1 plus 1T2. And if we omit the leading coefficients of 1, we get that it's simply equal to A1 plus T2. We expect to get 4 molecular orbitals because we started with 4 atomic orbitals. And this works out because T2 counts as 3 since it's triply degenerate. The irreducible representations that we found for the reducible representation tell us the symmetries of the molecular orbitals. Now we have to find out what the molecular orbitals actually look like. we need to make another table, but this table is a little different in that we need one column for each symmetry operation, not just one column for every class. So we're going to need a table that has 24 columns, since there are 24 symmetry operations in the point group TD. And here is where the fact that we have both C3 and C3 squared becomes important, as well as the fact that we have S4s and the S4 cubed, which is equivalent to the S4 minus 1. We need to include each of those in the table. So if it says that there are 6 C3s in a class, we need to show all of the C3s, keeping in mind that some of those C3s will be C3 squares. Similarly, for the 6 S4s, some of those S4s will be S4, and the others will be S4 cubes. Now we need to go through each and every symmetry operation of the group and see how it affects a representative orbital. The orbital we're going to use is sigma 1. So for each symmetry operation, we want to see where sigma 1 goes to. And we write that value down in the appropriate column of our table. To demonstrate the effects, we're going to show the unaltered sigma 1's position to the left, and then the position on the right will show to where sigma 1 is moved by the symmetry operation. So it's a left to right view here. So the first operation is the identity, and the identity keeps each orbital exactly where it was. So we start with sigma 1 and we end with sigma 1. So we're going to write down sigma 1 in the table. And here we see that we've written down sigma 1 under the identity operation. For the next two operations, we see C3 and C3 squared. The first C3 that we're going to choose is the C3 that actually goes through sigma 1. So sigma 1 being on the axis is not going to change for either C3 or C3 squared. So when you see the following two diagrams, they look identical because the effect on sigma 1 is identical for each of those. Sigma 1 gets rotated to sigma 3. Sigma 1 gets rotated to sigma 4. And we put sigma 3 and sigma 4 into the table. Sigma 1 gets rotated to sigma 2. And sigma 1 gets rotated to sigma 4. And we put those in the table as well. Sigma 1 gets rotated to sigma 2. Sigma 1 is rotated to sigma 3. And we put these values in the table as well. The next three symmetry operations are the C2s, the 180-degree rotations. First, we have the C2 around the z-axis shown here. Rotation around the x-axis takes sigma 1 to sigma 3. Rotation about the y-axis takes sigma 1 to sigma 4. And we write those into the table. In the following figures, see each of the S4 operations, all 6 of them, and as you go through each pair, once those are concluded, the appropriate entries will be entered into the table. The final 6 operations are the dihedral mirrors sigma d. So please see the following figures showing the effect on sigma 1 going from left to right is the effect of the symmetry operation, and then the appropriate value for the location of sigma 1 after the operation being entered into our table. Once we've completed the table, we add a second row, and this row will contain the characters from the character table for the irreducible representations that are in gamma sub sigma. We saw that it was equal to A1 plus T2, so first let's look at the A1 symmetry molecular orbitals. Since A1 is the totally symmetric representation, all the characters are equal to 1. So first we enter the red ones in the second row of our table for each and every symmetry operation. Then we do the same for the bottom part of the table. We multiply the numbers in red in the second row from the sigma characters in the first row to get the values in green in the third row. Essentially, it's going to be repeating the first row because we're multiplying each and every term by a positive 1. And we've shown that for the top half of the table. And here for the bottom half of the table for the irreducible representation A1. We take all of the terms in the third row, the green terms, and we add them all together. We notice that they total to 6 sigma 1 plus 6 sigma 2 plus 6 sigma 3 plus 6 sigma 4. then we can use the fact that if we have a solution to the Schrodinger equation, like a molecular orbital, then any constant factor of that solution is also a solution. Meaning that we can divide through by 6, essentially pull 6 out in front and divide by it, and we're left with our molecular orbital being sigma 1 plus sigma 2 plus sigma 3 plus sigma 4. If you have learned about normalization constants, then our normalization constant in front would be 1/2. If you haven't, it will not make any difference in our being able to draw out what the molecular orbitals look like for methane. And we have found the A1 symmetry molecular orbital so far. Because gamma sub sigma is equal to A1 plus T2, now we need to perform the same procedure for the T2 irreducible representation that we did for the A1 irreducible representation. So we are going to put the characters from the character table into our table here of the symmetry operations. It is important to be careful with the characters because in the character table for the point group, there is one character for each class. Here we have to be careful to put the appropriate character for each symmetry operation, knowing that the columns in the two different tables are not identically the same. So our first character is a 3 under the identity operation. In the TD character table, we see that the character for the 8 C3 operations for the T2 irreducible representation is 0. So be sure to put zeros under each and every C3 operation. One important fact to keep in mind is that in a character table, each of the operations in the same class have the exact same character, which is why in the TD character table, we can group together all 8 of the C3 operations into one class. Here we have to make sure we put a 0 for each C3. The character for the 3 C2s is -1, so we have to make sure that we write down in red the 3 -1s in each of the 3 C2 columns. The character for the 6 S4s is -1, so we are careful to put a -1, shown here in red, under each of the S4 and S4 cubed columns. Last but not least, the character for the 6 sigma Ds, the dihedral mirrors, is a 1, so we are sure to put a +1 shown in red in each of the 6 remaining columns of our table in the row labeled T2. Just as we did for A1, now we multiply the red numbers in the second row times the blue terms in the first row to yield the green terms in the third row. And we do that column by column, and using the fact that if we multiply anything by 0, the answer will also be 0. Next, we add all the terms in the third row that are green, just as we would add polynomials. So we add all the terms in sigma 1 with other sigma 1 terms, and we get 6 sigma 1 minus 2 sigma 2 minus 2 sigma 3 minus 2 sigma 4. Again, we can divide through by 2 to get this expression in lowest terms, which gives us 3 sigma 1 minus sigma 2 minus sigma 3 minus sigma 4, and this is shown in purple. Unlike the case for A1, this is not one of the molecular orbitals. Rather, it turns out that it is a linear combination of molecular orbitals, and we'll have to do a little bit of work to extract the forms for the correct molecular orbitals from this linear combination. If you draw this linear combination as if it were a molecular orbital, you would quickly notice that there are no atomic orbitals on carbon that have the proper symmetry to interact in either a bonding or an anti-bonding manner. The fact that we get this linear combination is a direct result of the fact that we have degeneracy in the point group and degeneracy in this particular triply degenerate representation. Therefore, we have to use the cause of degeneracy, the S4 and C3 operations, to solve the problem. Whenever we have a high order rotation axis that is either a C or an S rotation that is above 2, so we have either C3, C4, C5, S3, S4, S5, and so on, we will have as an inevitable consequence degeneracy. And to handle that in the projection operator method, we have to now use those symmetry operations to permute the combination that we've come out with so far and to subtract out linear combinations till we actually yield the correct molecular orbitals. So, what do we do? Well, if we use one of the S4 operations, we've already seen how S4 affects S1 in detail. So similarly, we want to see what happens to S2, S3, and S4 using the fact that the S4 operation is a linear operation. So the effect on S1 is, the effect on 3S1 is 3 times the effect on S1. The effect on S2 is equal to minus 1 times the effect on S2, and so on. We could use any of the S4 operations, but I'm going to use the one around the z-axis. So we would see that the first part, the C4, will turn C1 to the next corner, and then the reflection would take it to C3. So therefore, the effect on 3 sigma 1 would turn it into 3 sigma 3. Similarly, the effect on sigma 2 would be turned it to sigma 4, so the effect on minus sigma 2 would be minus sigma 4. And so on for the other 2 sigma orbitals, and we'll show the results in the next slide. When we apply the S4 operation on our green 3 sigma 1 minus sigma 2 minus sigma 3 minus sigma 4, the result is minus sigma 1 minus sigma 2 plus 3 sigma 3 minus sigma 4. Now it turns out that is not the orbitals we want, but we're now going to separate that expression in brown from the expression in green. The result of the subtraction is 4 sigma 1 minus 4 sigma 3, which is shown in red. we can divide through by 2 to convert this into the equivalent 2 sigma 1 minus 2 sigma 3. It turns out that this expression in red is not a molecular orbital either, as you would be able to determine if you draw it out and then try to find the appropriate atomic orbital on carbon, and there is none. So this is a linear combination as well, but we are closer to finding the actual molecular orbitals. What we do now is to write down our original linear combination in green, and then we're going to subtract from it the linear combination in red, and the result will be one of our 3 triply degenerate T2 molecular orbitals. The result, shown in black, actually is finally a true molecular orbital. We can interpret it such that any of the sigmas that have the same sign, so for example, both of the plus coefficients have the same phase, which we'll show later in one color. We can think of that as being the positive phase. And those sigmas that have a negative sign, a negative coefficient, have the same phase as each other, which we will think of as the negative phase, and we will later show in a separate color from the positive phase. So we see that in this combination, there are 2 atomic orbitals that have the same phase, and the other 2 have the same phase as each other. This is the first of the 3 T2 molecular orbitals. And then we will show how to find the other 2. To find the next of the T2s, we simply apply a C3 operation to each of the atomic orbitals that are in this linear combination, and we're going to use the C3 axis that goes through sigma 1. So all of the sigmas will be moved except for sigma 1. When we do that C3 operation, we get the second T2 molecular orbital, sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. If we apply the C3 operation to the second T2 molecular orbital, we get the third T2 molecular orbital, sigma 1 plus sigma 2 minus sigma 3 minus sigma 4. For the A1 molecular orbital, sigma 1 plus sigma 2 plus sigma 3 plus sigma 4, this corresponds to a situation where all the sigmas have exactly the same phase, shown in red. So we get this particular linear combination of group orbitals on the hydrogen atoms for the A1 molecular orbital. For the first of the T2s, we have sigma 1 minus sigma 2 minus sigma 3 plus sigma 4. So we show everything with a positive phase with a red filling, and everything with a negative phase with a purple filling. So this is the first of the T2 molecular orbitals. Here is the second of the T2 molecular orbitals, sigma 1 minus sigma 2 plus sigma 3 minus sigma 4, again showing by filling in red the positive phase and with a purple filling the negative phase. The third and final T2 molecular orbital is shown here, sigma 1 plus sigma 2 minus sigma 3 plus sigma 4. The only atomic orbital on carbon that has the proper energy and symmetry to interact with the same phase on all of the sigmas on hydrogen is the carbon 2s. If you recall that the s orbital is either all positive phase or all negative phase. So it can form bonding interactions in all four directions with each of the sigma orbitals. For the first of the T2 orbitals, the proper atomic orbital on carbon that has the correct symmetry is going to be the py orbital, because it has one lobe with a positive phase, which is red, and a negative phase, which is in purple. So we see that it has the same phase, same positive phase as S1 and S4, and the same negative phase as S2 and S3. And we see that there is a node following the node in the p orbital in the molecular orbital. So we see that the T2 molecular orbital has one node, whereas the A1 orbital had no nodes. Here for the second of the T2 molecular orbitals, the px orbital, the 2px orbital on carbon has the proper symmetry to interact with the hydrogen group orbitals. So we see that it has a positive phase in the proper direction to interact with sigma 1 and sigma 3, and it has a negative phase, which is the same phase as sigma 2 and sigma 4. Again, following the node in the 2px orbital, we have a node in the molecular orbital, T2. Since we only have one remaining atomic orbital on carbon, the 2pz, we hope that it has the proper symmetry to interact with the third T2 orbital, and it does. It has a positive phase that can interact in a bonding interaction with sigma 1 and sigma 2, and it has a negative phase, which is the same phase as sigma 3 and sigma 4, therefore being a bonding interaction in that direction. And as the other T2 orbitals have, it has a single node which follows the node in the 2pz orbital. Our final step is to make a qualitative energy level diagram. A1 molecular orbital, having 0 nodes, is expected to have lower energy than the 3 triply degenerate T2 molecular orbitals, which each have 1 node. In general, the more nodes, the higher in energy. And the 3 T2 orbitals, since they are degenerate, what that means is they have exactly the same energy, so they are shown horizontally at the same level in the energy level diagram. Methane has 8 valence electrons, 4 that came from carbon, and 1 each from each of the 4 hydrogen atoms, for a total of 8. And we can see that we can completely fill all of the bonding orbitals, A1 and the 3 T2s, completely with the 8 valence electrons. Since we're able to fill up all the bonding orbitals, and we have not filled up any anti-bonding orbitals, we would expect that methane would be a stable compound, which we know is true. I thank you very much for your attention for this very long video. Don't forget to like and subscribe. And as always, have a good one.